Hi guys, I'll go ahead and do another video. We'll continue with the schematic in a little bit, being there's not much left to do here, because kind of some of the other videos, in my last video we kind of went over some others, went over some of the detector and phase changer in the audio section, so a little more in depth somewhat. But all that's left really is, and we did do some work on this power supply, and we'll look at the I-tube. Now I made a video on what makes up an I-tube, how they're basically made and how they operate, and what makes them operate and stuff. So you can always look at that video as a reminder as far as the tube itself is concerned. I just want to point out on the I-tube how simple it is to, if you ever want to put one in a radio, or maybe you build a radio and you would like to add an I-tube or something of that nature, or you got a radio, which I've gotten before, that for whatever reason someone decided to cut the I-tube completely out and it was totally missing, and had to put a new one back in, rewire it back up and everything. And also understanding how they're wired helps you understand better if you have to troubleshoot one. Now the I-tube is actually very simple as far as the circuit goes and how it's connected up. We'll zoom in just a little bit on it and kind of get it centered here. So here's your basic I-tube 6U5. To hook one up, or how they're hooked up, first let's look at the heater chain. To hook one up, all you would ever have to do, most of your transformer radios, which is usually the ones that you will find I-tubes in or may want to add one to, generally the heater chain, one side is connected to ground, which you can see right here. This is your heaters going to the heaters. One side's connected to ground. So unless for various other reasons, as far as wire dressing goes, all the tubes, one side of the heater will be connected to ground, usually right at the socket, and just so that they just have one wire coming from the transformer and feeding through the various heaters. So the same thing can be done here with the I-tube socket. One side could be put to ground immediately, or in this case all I-tubes are connected that the cathode goes to ground, goes directly to ground. So you could actually connect here in the socket, just connect one side of the heater to the cathode. That'll take the ground part. The other side of the heater can just go wherever's convenient in the radio to connect it to your heaters. One of the tube sockets that might be real easy to connect up an extra wire right on the heater and bring it back to this, to the socket for the I-tube. So that takes care of that. Again, the cathode connected to ground. Any convenient place that you can find in the radio to connect to ground. You connect it to ground. What's next? Well, there's a 1 mega ohm resistor that runs from the plate to the target, and we talked about this. That's entirely always in the socket. They always put it right with the socket. It don't have to be very heavy. A 1/10 watt resistor does fine, so they're extremely small. They're easy to put in the socket or on the socket. So that connection, you just make that connection, put the 1 meg resistor in there. If you got a socket, it probably already is in there. So the only connection you got to make is from the target pin to B+, maximum B+, your full B+. In other words, here it's directly connected right to the output filter cap. Maximum voltage of 245 volts is going to it. So wherever that's convenient to connect to that B+, maybe going right back to that filter cap or some point where you got the full B plus, you can connect on. One wire left, grid. This has got to connect in the AVC circuit. Now, this radio actually has a dual AVCs coming off of one load resistor, but they split it, run two separate filters. In other words, 2.2 megs and a couple filter caps, 0.05 microfarad filter caps. It was a choice of their engineers to do that, and I think mainly because of the sophisticated circuitry dealing with the several bands, multi-band radio. So they decided to do it that way. Most radios is not done that way. You only got one single line that's running on the AVC. So the best place to find to connect a grid is look for the 2.2 meg. Now one side of that is going to go back and connect in to your IF can, the second IF can, or connect right near it, connect onto its wire. There may be a load resistor, maybe they're using the volume control as a load resistor, but it's going to be connected somewhere in that point. So you find that point. That's one side of the 2.2 meg. You don't want that side. You want the side that's connected to the 0.05 capacitor, and also the other side that feeds out and will go to the grid of the 6U, or of your IF tube. May not be a 6U7, but the IF tube, which is, that grid's connected to the secondary of the first IF can. You find the other side of that wire, that winding, that will be connected to that 2.2 meg, and will feed on over to either the mixer tube, or if you have an RF input tube such as this radio does here, it'll go to its grid. But you find that side of that 2.2 and you find a convenient place to connect the grid to it from the I-tube. Now generally in a lot of radios you'll find that this thing is mounted on, at least one end of it's mounted on a terminal strip, and usually both ends are. One nice thing about terminal strips, and in most radios you will find that resistor is connected on there. Some they don't have it connected that way, but most radios they will. The nice thing about terminal strips, and I've got one here, they'll wire up. Most of the time they'll wire just to the top parts of the terminal strips, like here. But where they're fastened onto the insulated material, they've got a hole. So as far as any of these connections, if you got, there's a terminal strip where you can make that connection, and that hole's open, you can just stick your wire in there and tie it in right there and solder it. Makes it real easy. So that's it for the I-tube. And so I just wanted to go over that, how they're connected in. They're not real difficult to connect one in. Don't take very many wires, and there's not much to that circuit. We'll briefly go over this power supply. We've been over it once before a little bit because we had a question about one time, and I did a video on that. This has a directly heated cathode, so I got a 5 volt on the cathode, but yet I'm pulling my B plus off. And here's my high tension or high voltage winding going to the plates. How can I be getting my high voltage here with 5 volts there? And we talked about that once before, and I kind of went over this. I've been over a little more, you know, with the filter caps in the last video, and the pi filter and stuff. So we're not really going to get too involved in this. In fact, actually I'm going to go over something else that deals with the power supply and deals with the radio entirely as a circuit. But this has just got a standard full wave rectifier We have 2 plates, center tap transformer. In this case, this transformer is going directly, the center tap goes directly to ground. Here's your 2 filter caps. They feed up and over to the socket plug. If you actually follow them through, what they're doing is one cap goes to one side of the speaker field winding, and the other cap, and that feeds out and comes to the output cap. This is just making up your pi filter. Here's they're using the speaker field, standard procedure in most radios, as a choke in the power supply. So instead of being drawn over here, they drew it over here since we've got a plug. Sometimes you'll see it more drawn in the schematic here, and other times drawn like this since there is a plug here. There's not much else to say on this. You got a 5-volt winding, you got your 6.3 volt windings, and then of course your primary winding on the transformer. Now, like I said, I'm going to go over something different that deals with power supplies and deals with the radio as a whole. So we're going to start that now. It's kind of help out somebody, but it's also to help everybody out. And I'm going to show, I drew up a real simplified drawing of a radio. I'll have to bring this out so it can be seen. And so I can tilt this up just a little bit. Okay. There's an extremely simplified drawing of a particular radio, and let's see if I can show that radio to you. I've got the schematic on the screen, and this is a Philco 39.7. What I did was I just got rid of all the most of all the resistors and other circuitry in here, and just mainly was interested in the active elements of the tubes, other than the grids themselves. The control grids are not drawn in. Our power supply, our bias resistors and stuff. Now, why am I doing this? Well, from time to time there's questions about what size wattage to use on these resistors. Maybe they're missing, maybe they're burned up, maybe they're been changed by someone else at some point, so you don't even know for sure. You don't have any schematic cross-reference telling you what size they should be as far as wattage and things of that nature. So we're going to discuss a little bit of power supplies and how they feed and how the whole thing works. And we'll go over that. Okay. The first thing I want to talk about, and let me get myself re-situated back onto this other drawing I did. Sorry about the quick movements. Okay, I want to talk about circuits and what is meant by the word circuit. And without sounding condescending or anything, but I think from what I have experienced in life, and anywhere from back in my teaching days to working with people on various things, and today in a lot of YouTube videos and everything, it seems like it can be somewhat a misunderstood word. So we're going to talk about first a real simple circuit, a flashlight. Now, let's discuss a little bit about the major components. If I was to ask you what is the major components, the electrical components of the flashlight, not any mechanical components, what would you say? What would you answer me with the major components? Well, most people would right off the bat say, well, you got batteries and you got to have a power source, so you got batteries. Alright, that's fine. And they may say that, well, you probably got a switch. Most flashlights do, so you have a switch. And then some form of lights. This has got LEDs, bulbs, LED lights in it. You know, some flashlights, older ones, had a single light bulb in them. And most of the time they'd stop there on electrical. The body of the flashlight is considered more of a mechanical thing. But is it really? Let's analyze it a little more. We know that the batteries go in the body. Well, let's see what we've got in here. Okay, we have, in this case, 3 batteries. They're connected end to end. And somewhere down inside there is a connector. Now that connector then hooks with a wire to the switch, and then another wire goes from there and hooks to this end, one end inside here of these LEDs. Alright, that's fine. So we have one connector down here for the batteries. Oops, and that won't work if I put it in that way. What about this end? Well, I had a cap on there. Well, that end of the connector, or connection to the batteries, is actually made through this spring, which in turn is in contact with this aluminum cap, which in turn is screwed on to the main body, which then is connected here by threads again, so that you can take it apart and you can pop it all apart and replace any components or clean the lens. Well, that screws onto here, and from inside there you can see a little spring and a circuit board. On one side of that circuit board there's a trace that goes all the way around that hooks to one side of the LEDs. That is making contact with that. The center spring one in there connects to the other side of the LEDs, which connect here, which connect to the switch. Well, what is that saying? Well, in the simplest terms, basically we have nothing more than right here in this empty space. I'll try to draw it in. And I'm just going to draw kind of a light bulb instead of LED. But we have some batteries. We have a switch. And that comes down and hooks into a light bulb. And that comes back. This return path here, or this path, is the bulb, or the body of the flashlight. What's the negative end of the battery? We had a spring here, we had another spring here, and we had the LEDs. This end is up inside the switch area, just this little area up inside here with contact on this end to hook the batteries, contact this end to hook to the little dinky spring that hooked the other side of the LEDs, and consequently some wiring to hook to the switch. When I flip the switch on, when it makes contact right through here, what happens is we get a flow, a current coming out, going through, goes through the light bulb and comes back to the batteries. That is a circuit. A circuit is a circle. It's closed loop and complete. Now, the point I want to make with this and is, if I was to put an amp meter right here and put an amp meter right here, both would read exactly the same. Whatever leaves the battery or the power source heads to the load must return from that load back to the battery. Now, a question is going to arise on that is, okay, that's fine. But if I turn this flashlight on, set it down, walk away from it. Now with LEDs it's going to take longer, but eventually it's going to go out. Right? You leave the flashlight on, the batteries eventually go dead. If what's coming out of the batteries, going through the light bulbs and coming back is the same amount of current, why is the batteries going dead? I should leave that as a question, but I won't. The reason is current is a carrier of energy. Current is nothing more than that. It carries energy. The batteries have a chemical energy. That's all that's inside that battery is two plates. They're different material, but there's two plates with a chemical electrolyte. The energy needed to light the light bulbs is a chemical energy. Okay? All current is doing is carrying that energy from the batteries to the light bulb. And yes, the light bulbs use an energy. Even LEDs get there's a little bit of heat loss and there's a lot of light. So we're giving off energy both in light and some heat. Depending on the light bulb, how much heat will be there is just, what kind of light bulb it is. But either way, we're losing energy. But it's energy that is being flown off into space. The heat goes off to heat the atmosphere and the surrounding area. Some of it radiates out and heats other things. Some by convection and so forth. Anyway, we won't get into how heat works, but that's thermodynamics. But anyway, the light itself, those photons fly out. They are absorbed by certain materials and they give off their energy to those materials. They go to your eyes. They react with your retina in the back of your eye. It absorbs them and they give off their energy there. The point is the current stays the same no matter what, but it's the energy that's being slowly taken out of the batteries to feed the light bulb. And that's the point I want to make on that point. The other point, the primary point, is what leaves the battery must come back to the battery and current. So now this brings us to our radio. Now, you have a power supply, a source of energy and current. It leaves out this point on the tube. It's coming through this winding, one side or the other, depending on which part of the cycle the AC is. Remember, it's a full wave. And it leaves here, goes through a filter, we've talked about that, and comes out and goes to our plate, or tubes. But some tubes have more than just one thing. Your output tube has a screen grid. That screen grid also gets a portion of the B+. This is the detector triode tube, so since it's just a triode, only a plate's there involved. The IF tube, another pentode tube, so it has a screen grid. So its you have a screen grid that's getting some B plus, and you have the plate that's getting some of the B plus. Your mixer tube actually has 3 actual main elements that are getting B plus. 3 connections. You have the plate, you have grids 5 and 3, and grid 2. Okay? Grid 2 is acting as a plate for a lower section of the tube, which makes up a triode for the oscillator. Remember, there's another grid in here that goes the other side, that goes the oscillator coil here. This is our feedback coil that's running off this other grid. That actually makes up a plate. So it actually has voltage, B plus voltage on it, because it's acting as a plate. These 2 grids work the top portion of the tube. This bottom one actually has less positive voltage than this grid has next to it, so it looks negative, so it acts as a cathode for, there's a control grid coming right in here. This one is just your screen grid, so it's got B plus on it, and then you got your plate. Now, why is that all important? Well, these, and I drew this out real simple. The tube, current flows through the tubes. Okay? All these grounds are connected together. So there's one side of the circuit, the negative side of the circuit. The positive side, everything is in parallel and connected back to one point where the B plus leaves last filter. Being that this all is parallel, all the currents, each one of these grids and these plates all draw, all add up. I haven't went over Kirchhoff's laws yet, and when I do you'll see it more, but in a parallel circuit voltages stay the same. That's why your house is wired parallel. Every outlet in your house is wired parallel to every other outlet in the house, in the circuit. That way, no matter which outlet you go, you get your 120 or whatever volts that your house normally has. But the currents, which are drawn, they're different. In a parallel circuit, the currents all add up. They split off down each branch as needed by draw, how much that branch needs to draw. And when they come back on the other side of the parallel lines where everything hooks back up, they add back together. Voltage stays the same, currents in a parallel, but current adds and subtracts. It splits down each leg. So the point is, and why we're discussing this, whatever feeds goes out here to all these circuits, all this, which is all really one huge circuit, all that B plus going out has to return back through these grounds back to the center tap of the transformer. So whatever amount of current's up here ends up coming back through here and through these resistors. Okay? Now how do I know what current? Tube manual. Without flipping the camera, and forgive me if I don't, on the schematic it's got various voltages. There's 135 volts for the plate. The screen grid's running at 145. This one's running at 75 volts. This is 145. The screen grid's 75. This is 145. This dual grid connection here is 75 volts. This is at 145 volts. So we got the voltages. We go to the tube manual. In the tube manual it tells us in the characteristics various voltages for various setups and the current draw of these active components, elements in here. So what you do is you don't go with 135 or 145, even if they're in there. Don't go with that. Always go a little higher. Go the next step higher is the best way to do it. So most of these tubes will have like 200 volt section underneath where you can look up in the characteristics, and it'll give like on this tube here, which is the 41, it'll give you the plate current at that voltage, and if you got the screen on the same voltage, it'll tell you at that voltage what kind of current it has. Just add them together. This 6Q, no, it's 75 tube, same thing. It has, go to its about maximum voltage in the characteristics, see what current that plate draws. Add that to these. Same thing with this tube here, which is a 78. You'll have current for the plate, current for the screen grid. Again, add them together and add them to the other tubes. And the same thing with this tube, the 6A7. You get all these currents added together, and that will be the current that will be going back through these resistors. Now again, we went with higher voltages because there is some loss in other parts of this. These resistors are going to heat a little bit, so there's going to be some loss there. There's some other components that you've seen in the schematic I didn't draw on here. They'll have a little bit of current droppage, you know, the IF coils, the output transformer coil, they all got some DC resistance, which will drop a little bit of voltage and drop some heat. So that's why we always go up a step or two. It's better to do that. All you end up doing is you might end up putting a higher wattage resistor in necessary, but that's fine. Higher wattage is not any more, there's not that much difference between, say, a 1 watt resistor and a half watt resistor. And size wise, matters not. Because you can get 1 watt resistor that's smaller than a half watt. So we always want to go up, not down. Or not at least try to keep it close or second guess it at the closest point. So, but the point is, whatever current that everything in here is drawing is all added together and comes back through here. And at that point, now you know from the schematic. The schematic tells you the resistance. Okay, which is fine. You can use that resistance or whatever resistor that you're going to replace it with. You know, in this case, this radio uses a 250 ohm. That might be a little difficult to find, but the next best one is 270 ohm. Use that size resistance. I squared R. Now this is series here, so the current is the same between these two resistors. This current will be the same. So I squared R gives you wattage. So you take the current times itself times whatever resistance is will be whatever wattage you need. And then go up a little bit. If it's like, say you came out with 0.48 watts. Well, yeah, you could use a half watt. And a half watt resistor will handle just fine all day long, a half watt. But if you put a 1 watt in there, it'll just last longer. Because anything, if you're always pushing it, just like your car. Yes, your car red lines at, say, 5,000 RPM. But if you ran it every day, all day long at 5,000 RPM, it's going to wear out a lot sooner. Well, resistors are no different. Run them at a half watt resistor at half watt all day long is going to wear it out a lot quicker than if you had a 1 watt in there running at a half watt. So if it comes out like, say, 0.48 watts, put a 1 watt in. It's not going to cost you really any more money, and maybe a couple pennies at the most more, and it's going to fit in there just fine. But the point I wanted to make out is whatever's going to the tubes, whatever leaves here comes back through here. Same amount. So that's what a circuit is. So that's really, I hope you guys all understood this and stuff, and how to figure this and how to look it up. Again, tube manuals, you can look up your tubes and look up the current for your screen grids, your plate, and so forth. Whatever current handling elements. and for the, a certain voltage on them, and you can, make sure you remember to add them all together and stuff. So anyway, I hope you understand that, and if you have any questions, just leave them in the comments, and I'll make another video to discuss those. So this is another long video, sorry about that. So anyway, thanks for watching, and I'll see you in the next one.